about logarithms in section 2. So basically, and I know this is going to be somewhat of a review from last year. So basically, here's what you have, right? You have powers of 2 here. And if you have 2 to the 1, we get a 2. 2 to the 2, you get 4. 2 to the 3, you get 8. So we increase the exponents, from 1 to 2 to 3. Our value jumped from 4 to 8. What if, though, I wanted to raise 2 to a power of something and get 6? What would that exponent be? Now, you can probably tell it's going to be somewhere between 2 and 3, right? And then, we could laboriously figure it out. Is it 2.5? Is it above 2.5? Blah, blah, blah. But basically, the answer to that is a logarithm. Okay? So when we take a logarithm, what we're looking for is the exponent, so that 2 to the power of something is 6. All right? And I really like to stress this to my students, that a logarithm is just an exponent. Okay? All right. So if you're walking down the street, okay, and somebody taps you on the shoulder and says, what is a logarithm? You should just say exponent. It's an exponent. Right? Okay. So that's why we can write the same thing in logarithmic form and exponential form. So let's look at the exponential form for a minute, because that's easier for us to figure out. B to the y is equal to x. B is the base, y is the exponent, and it equals to x, right? So I can write the same thing as log base b of x equals the exponent y. The answer to a logarithm is always the exponent, okay? So here we go. Answer to a logarithm is an exponent. So if I were walking down the street and I saw this on a billboard, okay, in my mind, that would register as, where's the base here? Where's the base? Is it the 9 or the 3? Log base b. It's the 3. In my mind, this registers as 3 to the power of what equals 9. Okay? So if I were walking down the street and I saw this, in my mind, 5 to the power of what is 125. Okay? That's what I see in my mind. So now here, take a look at this then. Log base b of 1. B to the power of what gives you 1? 0. Okay? Take a look at the second one. Log base b of b. B to the power of what gives you b? 1. Okay? Here, what should the exponent of b be so that I get b to the x? X. So the answer is x. You see what I mean? All right? And this is just the inverse of that. So b log b of x is x. Okay. Common logarithms is when you have log base 10. Log base 10. So log base 10 of x, we just write it as log of x. So in here, when you don't have a base explicitly written to you, you know that the default base is 10. So when I see this, I imagine a little 10 here, and in my mind, I'm like, okay, 10 to the power of what is 1? 0. Okay? So when I see this, I imagine a little 10 here, and in my mind, I'm like, okay, 10 to the power of what is 10? 1. You see? So here, 10 to the power of what gives me 10 to the x? X. Okay? All right. Let's do some logarithms. Imagine, so here we have some logarithms and we're going to look for the answer. What's the answer to a logarithm always? An exponent. So what should the exponent of 2 be in order for me to get 16? 4. Okay, so do we see how we think about them? Okay. What should the exponent of 5 be in order for me to get 1 over 125? Negative 3. Right? So when you're going between a whole number and a fraction, it's a negative that does that. The simplest way is, okay, how do I go from 5 to 125? Exponent of 3. How do I make the whole number a fraction? Negative. Okay, what about this one? So this is really log 3 of 3 to the half. So it's 1/2. Okay? So root 3, another way to write root 3 is 3 to the half. So now I say, what should the exponent of 3 be? So I get 3 to the half, 1/2. Okay? All right. 8 to the 512. 8 to the what gives you 512? Is it 4 or 3? 3? 4 just seems too big. Okay, when you have something like this, 22 log 22, it just goes away. And we have 15.5. What's the base for f? 10. What should the power of 10 be to get 10,000? 10 to the, so basically this is a 10. So the question is 10 to the what is, 10 to the what is 10,000? How many zeros are there? 4. So it's 4. Okay? 10 times 10 is 100. 10 times 10 times 10 is 1,000. What's the next one? G. 12. Because 10 log 10 goes away. Okay, so the next one, log 14, there is no common base there. So you are going to have to plug that into your calculator. Okay, because you can't do, mentally, you can't do 10 to the power of what gives you 14. So just press log 14. 3 decimal places. 1 point. What about log of negative 12? Doesn't exist. No solution. Because log is only defined for positive values, right? So because the logarithm is an exponent, you can never raise something to an exponent and get a negative number, right? Okay. Now, so we talked about log with a random base, b. We talked about log with a base of 10. What about, remember that special number e? What if we have log base e of x? Well, this is such a natural occurrence that we call this the natural log. Instead of writing log base e, a synonym for it is ln of x. So log base e is just ln. Okay? And in the same way, so if I have ln of 1, that's like saying log base e of 1. And the question is, e to the power of what gives you 1? 0. So ln of 1 is 0. Okay? ln of e is 1. ln of e to the x is x. ln of e just go away. So let's do some examples here. What would this turn into?
4.5.
And b? Can't, no solution. And c? E to the ln?
4.
Just 4. And this one, we plug it in and we get
1.946.
awesome. Okay? All right. Now, we're going to graph logarithmic functions. Now, if So the answer to a logarithm is an exponent, right? Another way to think about that is logarithms and exponentials are inverses of each other, okay? So remember yesterday we were graphing the exponential functions? That's how they look. And now we're going to graph logarithmic functions. Do you remember how we talked about the fact that if two functions are inverses of each other, they are symmetric along the line y equals x? Look at that. Look at the symmetry. Look at how beautiful it is, right? So because then exponentials and logarithms are inverses of each other, all of those properties between inverses will apply. How do you find the inverse of a function? What's the first step? You interchange what and what? You interchange x and y. And when we interchange x and y, what happens to the domain and range between inverse functions? They switch. Okay? So, let's remind ourselves. This is why I stressed that stuff before, right? So let's remind ourselves. If you have y equals e to the x, okay? What's the domain? Negative to positive infinity, the domain. And what's the range? 0 to infinity. And it has a horizontal asymptote, right? Well, the logarithm has a vertical asymptote. And so if we have y equals ln of x, the domain is now 0 to infinity, and the range is all reals. Okay, that's why I was stressing that yesterday, okay? That when you see a function, you should figure out what the range is, what the domain is, because now you have to do it for the same thing with the logarithms, okay? So you see then that the logarithm has a vertical asymptote here, and you can only have positive values of x. That's why log of -2 doesn't work. Log of 0 doesn't work, right? Because x can't be 0 for a logarithm. That's a vertical asymptote, okay? So let's take a look at these functions now. We're going to graph log base 2 of x, okay? Now, what is a logarithm? What is the answer to a logarithm? An exponent, right? So if I have y equals log base 2 of x, what's the y? The y is the exponent, right? The y is the exponent. What's the base? What's the base? 2. So let's think about powers of 2. Remember I was trying to do that yesterday? What are the powers of 2? 2 to the 0 is 1, and then it's 2, and then 4, and then 8, and then 16. And what if we're going in the other direction? 1/2, 1/4, and so on and so forth. Okay, so good. So remember how we said the y is always the exponent? So if the y is the exponent, -1, 0, 1, 2, 3, okay, these are the exponents. Then what are the powers? 2 to the -1, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Do you see how we did that? Okay, and now we can graph our logarithm. Okay, what's the asymptote? Is it horizontal or vertical?
Vertical.
Vertical, so it's x equals 0. I love this stuff. I don't get to teach this as much as I would like. So when I teach it, I love it. Okay, so when x is 1/2, we're at -1. Yeah, so the y's are the exponents of 2. And here we have 2 to the -1, 2 to the 1, 2 to the 2, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 4. Okay? It's 2 to the 3. Okay? So, when x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. When x is 8, y is 3. Okay, and you know there is an asymptote here. So look. You see that? Isn't that cool? The asymptote? All right, so what's the domain then? The domain is 0 to infinity. The range is all reals. There is no y-intercept this time. There is an x-intercept, right? At 0 and 1, 1 and 0. Okay. Let's talk about left and right limits. So the right limit, as x approaches infinity, y goes to positive infinity. Now, in this case, it doesn't make sense to say what happens as x approaches negative infinity because it can't cross 0. Instead, we're going to get into more detailed versions of this. We say what happens as x approaches 0 from the positive side. So as x approaches 0 from the positive side, what's happening to the graph? It's going down to negative infinity. And it's continuous everywhere on its domain, which is from 0 to infinity. All right. All right, so let's do another one. 1/3 is the base. Okay. So the asymptote again is x equals 0. Now, again, the y values are going to be our exponents. All right. So let's do exponents of, let's say, -2, -1, 0, 1, and 2. Okay. So what are we going to get here? 1/3 to the -2, 9. 1/3 to the -1, 3. 1/3 to the 0, 1. And then 1/3, and then 1/9. Okay. So when x is 9, y is -2. When x is 3, y is -1. When x is 1, y is 0. When x is 1/3, y is 1. And then it's 2 here. So look at which way this goes. Okay, that way. So this is the difference between like the growth and the decay, right? Okay. So the domain, same thing. The range, same thing. The x-intercept is 1, 0. Okay, so what happens as the limit to the, what's the limit as x approaches 0 from the positive side? Infinity. And as x approaches infinity, negative infinity. And it's continuous everywhere on its domain. Okay. Yeah. Next one is ln. So what's its base? E, right? So we're going to do powers of e to the 1, e to the 2, e to the 3, e to the 4. And here we have our exponents. Now, what about this -6? What does that do to the graph? Where does it move it? Shifts it right. How many units? 6. So the asymptote would have been at x equals 0. Where is it now? At x equals 6. So now, the base here is e, right? So what we're going to do is e to the negative 2, e to the negative 1, right? These are the exponents, e to the 1, e to the 2, but then we're going to shift it to the right 6, okay? And I want you guys to be able to do this like mentally. So let's start from the middle. What's e to the 0? 1, but then we have to move it over 6, so it's 7, right? E to the 1 is 2.7, 8.7. E to the 2 is 7.4, so it's, right. And then what's e to the minus 1? Or 1 over e? How much is it? Right, so it'll be 6.4. Oh. Oh my. So then what's e to the minus 2? So it's 6.1. Okay. That's 0.135.
Oh, this is 1.1.
Okay. So now, when x is 6.1, we're at negative 2. 6.4, we're at negative 1. 7, we're at 0. 8.7, we're at 1. And then 13.4, we don't have room for. So basically, it's going to look like this. Okay? So the domain is going to be 6 to infinity. The range is all reals. The x-intercept is 7, 0. And here, okay, so I have a typo here. This should say 6 plus, right? So as it approaches 6, it goes to negative infinity, positive infinity over there, and it's continuous everywhere on its domain. It can be, the intensity level of sound can be modeled by this formula here. W is the intensity, and it's watts per square meter. W naught is a constant. So here it says, if the intensity of sound of a person talking loudly, which is what I'm doing right now because I'm so excited about this math, is that many watts per square meter, what is the intensity level in decibels? Okay? So what we're going to do is D of W is 10 log, right? So what this is, the intensity of sound, this is W. So it's 10 log 3.6 times 10 to the negative 8 over, what was the constant? 1 times 10 to the negative 12. Okay? And you remember in science, no, because it's the logarithm of that.
Oh, it's not. Okay.
It's going to be 45 when you work it out. Okay? So 45 decibels. So if your sound has an intensity of that many watts per square meter, 3.6 times 10 to the negative 8, it's 45 decibels. Okay? So it's the intensity versus the decibel level. Now, if the threshold hearing of a certain person with hearing loss is 5 decibels, so they have to have at least 5 decibels for them to begin to hear you, will a sound with this intensity level be audible for that person? So let's see how many decibels that translates to. So here, D of W is going to be 10 log 2.1 times 10 to the negative 12 over 1.0 times 10 to the negative 12. Here is where your chem knowledge, right? Your math, your chemistry math, right? You could cancel those out. So we have 10 log 2.1, you plug it into the calculator, and this is 3.22 decibels. So will this person be able to hear this? No. Okay. Well, I guess that's either good or bad, depending on what you're talking about. If you're playing some horrible music, I guess it's not that bad that they can't hear it. Right? Okay. So sound in excess of 85 decibels can cause hearing damage. What should the intensity of sound be for a level of 85 decibels? Right? So now we're going the other way. So 85 is equal to 10 log W over this constant. Huh? You can. So 8.5 is equal to 10 is equal to log oops 1. Now what's the base here? 10, right? So how are we going to solve this? Right, 10 to the power of 8.5 is equal to W over 1 times 10 to the negative 12. So then when we multiply, W is equal to 3.2 times 10 to the negative 4 watts per square meter. All right, so this homework will be due tomorrow.